In the meticulously choreographed theater of a modern military parade, every polished bolt and gleaming panel is a carefully crafted line in a geopolitical script. Amidst the expected procession of sleek, solid-fueled road-mobile launchers, the very picture of 21st century strategic agility. The appearance of a system with design roots stretching back to the 1960s can be jarring. Yet, when the Dongfeng 5C, DF-5C, rolled through Tiananmen Square, disassembled into 3 massive sections on separate transporters, it was not an anachronism, but a profound statement of intent. It was a deliberate message that forced a global recalculation of strategic threat assessments, demonstrating that in the high-stakes calculus of nuclear deterrence, the age of a design is a trivial matter compared to its continuous, calculated evolution. The DF-5C, a direct descendant of China's first true intercontinental ballistic missile, ICBM, represents the apotheosis of a particular strategic philosophy, one that is patient, iterative, and brutally pragmatic. It is not a weapon born of a desire for technological novelty, but rather a purpose-built instrument designed to solve a specific and existential problem: how to guarantee devastating retaliation in the face of an increasingly sophisticated, multi-layered ballistic missile defense (BMD) shield. The continued and indeed escalating investment in this liquid-fueled behemoth is not a sign of technological stagnation, but a deliberate strategic choice. It is a conscious trade-off, sacrificing the rapid response capabilities essential for a surprise first strike in favor of the one attribute that liquid propellants provide in abundance: a colossal throw weight. This immense payload capacity is the key that unlocks the DF-5C's true purpose: to carry not just multiple warheads, but a bewildering array of advanced penetration aids, decoys, and chaff sufficient to overwhelm and saturate any conceivable defense system through sheer mass and complexity. The DF-5C is, therefore, the physical embodiment of China's doctrine of assured retaliation. Its very design, ponderous but powerful, signals a defensive second strike posture, a weapon ill-suited for a bolt from the blue attack, but perfectly engineered to ensure that any aggression against the homeland would be answered with an unstoppable storm of nuclear fire. The story of the Dongfeng 5, which translates to East Wind 5, is the story of China's strategic deterrent itself. Its development began in the mid-1960s, a product of the ambitious Banyan Sedan, 4 missiles in 8 years, plan, which aimed to systematically develop a family of ballistic missiles with progressively longer ranges. The DF-5 was the culmination of this effort, designed to integrate the lessons learned from earlier systems like the DF-3 and DF-4 into a true intercontinental weapon capable of holding the continental United States at risk. After a protracted development period marked by the disruptions of the Cultural Revolution, the DF-5 conducted its first flight test in 1971 and a full-range test into the Pacific Ocean in May 1980, finally entering operational service in 1981. The initial DF-5 was a classic Cold War deterrent, a 2-stage silo-based giant standing 32.6 meters tall and weighing 183,000 kilograms. It was designed to deliver a single, massive thermonuclear warhead with a yield estimated between 3 and 5 megatons, a city-destroying weapon of terrifying power. Its range of 10,000 to 12,000 kilometers was sufficient to target the western portions of the United States, establishing for the first time a credible, albeit limited, Chinese nuclear deterrent against a superpower adversary. The first significant evolution of the platform came in the mid-1980s with the development of the DF-5A. This upgrade was a straightforward enhancement of the original design's core capabilities. The range was extended to over 15,000 kilometers, bringing the entire continental United States, including the eastern seaboard, comfortably within its targeting envelope. This was accompanied by an increase in throw weight, from an estimated 3,000 kilograms to over 3,200 kilograms, and improvements to its guidance system. For nearly 3 decades, the DF-5A, with its single, powerful warhead, formed the backbone of China's intercontinental retaliatory force. However, the strategic landscape began to shift dramatically in the early 2000s, particularly after the United States' withdrawal from the Anti-Ballistic Missile (ABM) Treaty in 2002 and its subsequent investment in a national missile defense system. This development posed a direct threat to the credibility of China's small, single-warhead ICBM force, raising the possibility that a limited retaliatory strike could be intercepted and neutralized. Beijing's response was methodical and deliberate, culminating in the public unveiling of the DF-5B at a military parade in 2015. This variant marked a revolutionary leap in capability, introducing multiple independently targetable reentry vehicle (MIRV) technology to the Dongfeng family for the first time. The DF-5B transformed the monolithic weapon into a Hydra, capable of carrying between 3 and 8 smaller nuclear warheads, each of which could be directed to a separate target. This move was a direct answer to the challenge of missile defense. A single DF-5B launch could now present a defensive system with multiple incoming threats, vastly complicating the task of interception and ensuring a higher probability of at least some warheads reaching their targets. The upgrade also included a more advanced guidance package, improving the missile's accuracy to a circular error probable (CEP) of approximately 300 meters, a significant improvement over the original's 800 meters. This evolutionary timeline reveals a distinct pattern of reactive modernization. China possessed the core technologies required for a MIRV system for decades. Its space program demonstrated the ability to launch multiple satellites from a single rocket, a feat functionally equivalent to deploying a MIRV bus as early as 1981. Yet, it refrained from weaponizing this capability on its ICBMs for over 30 years. The deployment of the MIRV DF-5B was not a proactive attempt to gain a first strike advantage, but a calculated countermove, an insurance policy taken out only when the strategic stability that underpinned its deterrent was perceived to be eroding. The DF-5C is the next logical step in this evolution, a further refinement designed to maximize the saturation capability and guarantee the enduring potency of the east wind. A detailed examination of the Dongfeng 5C reveals a complex interplay of legacy architecture and cutting-edge subsystems. It is an engineering marvel not of revolutionary design, but of persistent and intelligent adaptation, where the inherent limitations of an older system are mitigated or even turned into strengths through targeted modernization. From its colossal airframe and volatile propulsion system to its remarkably precise guidance package, the DF-5C is a case study in maximizing the potential of a proven platform. Structurally, the DF-5C retains the foundational architecture of its predecessors. It is a 2-stage liquid-fueled vehicle with a commanding presence, maintaining the family's approximate dimensions of 32.6 meters in length and 3.35 meters in diameter, with a launch mass of around 183,000 kilograms. The first stage, responsible for the immense task of lifting this behemoth from its silo, is powered by a cluster of 4 gimbaled engines, a design that provides both the raw power and the control authority needed during the initial phase of flight. The heart of the DF-5C, and the source of both its greatest strength and its most significant operational weakness, is its propulsion system. It relies on a hypergolic, storable liquid propellant combination, unsymmetrical dimethylhydrazine, UDMH, as the fuel and nitrogen tetroxide, NTO, as the oxidizer. The term hypergolic means the two components ignite spontaneously upon contact, a property that greatly simplifies engine design by eliminating the need for a complex and potentially failure-prone ignition system, a crucial advantage for reliability. However, this chemical convenience comes at a steep price. These propellants, sometimes referred to by launch crews with a gallows humor as devil's venom, are extraordinarily hazardous materials. Both UDMH and NTO are highly toxic, deeply corrosive, and carcinogenic. Handling them requires extensive, specialized infrastructure, full-body hazardous material suits for personnel, and a pre-launch fueling process that is both time-consuming and fraught with risk. This procedure, which can take anywhere from 30 to 120 minutes, stands in stark contrast to the near-instantaneous launch readiness of solid-fueled missiles like the American LGM-30G Minuteman III. This lengthy pre-launch ritual, requiring more in common with 19th century industrial chemistry than 21st century rapid response, makes the DF-5C inherently unsuitable for a first strike, as it would be a vulnerable target during its lengthy preparation phase. Recognizing this vulnerability, Chinese engineers have implemented an ingenious, if partial, solution for the DF-5C. As displayed in its parade debut, the missile employs a modular transport system. The entire airframe is broken down into 3 sections: the first stage, the second stage, and the payload shroud, each carried on a separate heavy transport vehicle. This approach is intended to reduce the time required for on-site assembly and preparation within the silo, thereby shortening the overall launch sequence and improving its responsiveness compared to older models. While it does not eliminate the fundamental delay associated with liquid fueling, it represents a pragmatic effort to streamline the process and narrow the readiness gap, making the silo sitter slightly less sedentary. If the propulsion system represents the DF-5C's brute force, its guidance package embodies its surgical precision. The missile employs a sophisticated, multi-layered guidance system that blends Cold War-era reliability with modern, network-centric technology. The foundational layer is a fully autonomous inertial navigation system, INS, composed of high-precision gyroscopes and accelerometers that continuously calculate the missile's position, orientation, and velocity without any external input. This is supplemented by a starlight guidance system, or astronavigation, which uses star trackers to take celestial sightings during the mid-course phase of flight, allowing the onboard computer to correct for any accumulated drift in the INS. This combination of self-contained systems makes the missile highly resilient to electronic warfare, such as GPS jamming. Layered on top of this robust foundation is a modern augmentation system that links the missile to China's Beidou satellite navigation constellation. By receiving precise timing and positioning signals from the Beidou network, the missile's flight computer can continuously update its position and velocity, correcting for even minute errors in the inertial platform. This hybrid approach provides the best of both worlds: the jam-proof autonomy of an INS and the pinpoint accuracy of satellite navigation. This technological fusion has resulted in a dramatic improvement in precision. While the original DF-5 was a relatively blunt instrument with a CEP of around 800 meters, the DF-5C is reported to have achieved a CEP of 300 meters or less. The technical achievement of guiding a 183-ton vehicle traveling at speeds exceeding Mach 22 to strike within a few city blocks of a target over 15,000 kilometers away is nothing short of extraordinary. Chinese state media has even boasted that the missile's accuracy at intercontinental ranges is comparable to that of its mid-range systems. This leap in precision fundamentally alters the strategic role of the DF-5C. It is no longer merely a counter-value city buster. Its newfound accuracy gives China a credible counterforce capability, enabling it to reliably target hardened military installations such as enemy command centers and, most significantly, other nations' ICBM silos. This complicates an adversary's strategic calculus by putting their own nuclear forces at risk, thereby enhancing deterrence not just by threatening populations, but by threatening the adversary's very ability to wage nuclear war. The ultimate purpose of the DF-5C's immense structure and sophisticated guidance is to deliver its payload, a formidable package of nuclear warheads and penetration aids designed to guarantee a successful strike. The business end of the missile represents the culmination of decades of Chinese research into warhead miniaturization, post-boost vehicle technology, and the extreme materials science required to survive the violent inferno of atmospheric re-entry. The defining feature of the DF-5C's payload is its capacity to carry a large number of MIRVs. Reports from its 2017 test launch and subsequent analyses indicate the missile is equipped to carry between 10 and 12 independently targetable warheads. This represents a substantial increase over the earlier DF-5B and is the core element of its strategy to saturate and defeat missile defense systems. The key to this capability is a highly advanced upper stage known as a post-boost vehicle, PBV, or more colloquially, a bus. After the main two stages of the rocket have expended their fuel and separated, the bus, carrying the entire complement of warheads, continues on a ballistic trajectory into space. Using its own small precision thrusters and an independent guidance system, the bus performs a series of carefully calculated maneuvers. It orients itself, releases a single re-entry vehicle on a precise trajectory toward its designated target, then reorients and adjusts its course to release the next warhead toward a different target, repeating this process until its entire payload is dispensed. China's mastery of this complex technology is not a recent development. The nation's space program has long demonstrated the prerequisite skills by successfully launching multiple satellites into different orbits from a single rocket, a procedure that is functionally identical to the operation of a MIRV bus. This deep well of experience has allowed the People's Liberation Army Rocket Force, PLARF, to develop a highly capable and reliable PBV for its flagship ICBM. Furthermore, the DF-5C's payload is not limited to nuclear warheads. The system is designed with flexibility in mind, allowing for a mixed load that can include a suite of sophisticated penetration aids. These can range from simple chaff, which creates a cloud of metallic strips to confuse radar, to advanced decoys such as inflatable balloons, shaped like re-entry vehicles, or sophisticated electronic jammers, all designed to overwhelm an enemy's sensors and make it impossible to distinguish the real warheads from the false targets. The DF-5C's massive throw weight is a critical advantage here, as it allows for the deployment of not just more warheads, but also heavier, more complex, and thus more convincing decoys than could be carried by a smaller, solid-fueled missile. This turns each launch into a complex shell game played out at hypersonic speeds in the upper atmosphere, maximizing the probability of a successful strike. Each of the DF-5C's warheads is housed within a re-entry vehicle, RV, a marvel of material science and aerodynamic design engineered to protect its deadly cargo during its final fiery plunge through the atmosphere. As an RV re-enters the atmosphere at speeds exceeding Mach 20, it compresses the air in front of it, creating a shockwave that heats the surrounding air to thousands of degrees Celsius, enveloping the vehicle in a glowing sheath of ionized gas or plasma. To survive this environment, where temperatures can exceed 3,000 degrees F, the RV is protected by an ablative heat shield. This shield is not designed to insulate the warhead, but to actively dissipate heat by charring, melting, and vaporizing in a controlled manner. As the outer layers of the shield burn away, they carry the intense thermal energy with them, keeping the internal temperature survivable for the warhead and its sensitive fusing mechanisms. The performance of this heat shield is entirely dependent on the advanced materials from which it is constructed. While early RVs used materials like phenolic resins or even specially treated wood, modern high-beta, slender and fast RVs require far more advanced composites to withstand the higher heat loads and maintain aerodynamic stability. Western intelligence assessments have long indicated that China has placed an exceptionally high priority on the research, development, and acquisition of carbon-carbon composite technology. This material, consisting of carbon fibers woven into a three-dimensional matrix and reinforced with carbon, is exceptionally strong, lightweight, and maintains its structural integrity at extreme temperatures. It is particularly well suited for the nose tip of an RV, the component that experiences the most intense heating and aerodynamic stress. China's demonstrated progress in the broader field of hypersonic material science, including the development of non-ablative surfaces for reusable hypersonic vehicles, suggests a deep and mature industrial base capable of producing the sophisticated composites needed for the DF-5C's re-entry vehicles. The ability to manufacture these components indigenously is a critical element of China's strategic independence, ensuring that its ultimate deterrent is not reliant on foreign supply chains for its most critical components. The physical characteristics of the Dongfeng 5C are inextricably linked to its operational doctrine. As a massive, liquid-fueled missile, it is confined to a static, silo-based deployment posture, a method that presents both significant vulnerabilities and unique strategic opportunities. China's approach to operating the DF-5C fleet reveals a sophisticated understanding of these trade-offs, leveraging hardening, dispersal, and large-scale deception to create a survivable second strike force that is far more resilient than a simple accounting of its launch platforms would suggest. The DF-5 family has, since its inception, been deployed in hardened underground silos located in central China, designed to withstand the blast and overpressure effects of a nearby nuclear detonation. For decades, the PLARF maintained a relatively small and stable force of approximately 20 operational DF-5 launchers, a posture consistent with a minimal deterrent strategy. However, in recent years, commercial satellite imagery has revealed a dramatic and unprecedented shift in this doctrine. A massive construction program to build hundreds of new ICBM silos across vast fields in western China, including at sites near Yumen-Hami and Hangan-Banner. This undertaking, described by analysts as the most significant expansion of the Chinese nuclear arsenal ever, fundamentally alters the survivability equation for its land-based forces. The sheer number of these new silos, estimated to be at least 250, far exceeds the number of new ICBMs China is projected to build in the near term. This disparity strongly indicates that Beijing is adopting a shell game strategy, formerly known as a multiple protective shelter, MPS, basing mode. This concept, which the United States explored for its MX missile during the Cold War, involves building a large number of silos to house a much smaller number of actual missiles. By periodically and secretly moving the missiles between these silos, the PLARF creates a profound targeting dilemma for any potential adversary. To be confident of destroying China's silo-based force in a disarming first strike, an attacker would no longer be able to target 20 known locations. They would be forced to target all 250-plus potential locations, expending a vast and likely prohibitive number of their own strategic warheads to do so. This strategy is augmented by the long-standing Chinese practice of constructing decoy silos, less complex structures designed to mimic the appearance of an operational silo to further complicate adversary intelligence and targeting efforts. This silo shell game is a form of asymmetric deterrence achieved through concrete, steel, and deception. It is a cost-imposing strategy that forces a potential aggressor to either invest massively in intelligence, surveillance, and reconnaissance (ISR) assets to track the real missiles in real time, or to plan for a counter-force strike of such a scale that it would be strategically and politically untenable. This focus on survivability highlights a central operational paradox. Official Chinese commentary often describes the DF-5C as being on constant alert, ready to defend the nation at all times. Yet, this claim is at odds with the physical reality of its liquid fueling process, which renders the missile inert and highly vulnerable for up to 2 hours prior to launch. In a crisis, this delay could be fatal. This inherent vulnerability is likely a key driver behind a potential shift in China's nuclear posture toward a launch on warning, low policy. A low posture would mean launching its ICBMs upon receiving reliable warning of an incoming enemy missile attack, before those missiles could be destroyed in their silos. Such a policy is critically dependent on a highly effective and redundant missile early warning system. It is in this context that reports of Russian assistance in helping China develop a space-based early warning satellite network become particularly significant. A robust early warning capability would give Chinese leadership the confidence to ride out an attack until the last possible moment, or to launch its retaliatory strike while enemy warheads are still in flight, thus ensuring the survival of its silo-based deterrent. To fully comprehend the significance of the Dongfeng 5C, it must be placed within the global strategic context, measured against both the sensational claims made about its capabilities and the real-world performance of its primary American and Russian counterparts. This comparative analysis reveals that the DF-5C is not simply a Chinese version of an American or Russian ICBM, but the product of a distinct design philosophy tailored to a unique set of national security requirements. During its public debut, Chinese state media and affiliated military experts made the striking claim that the DF-5C possesses a range in excess of 20,000 kilometers, a distance sufficient to provide global coverage and strike any point on Earth from launch sites in northern China. This figure is a significant leap from the 13,000 to 16,000 kilometer range, typically attributed to the DF-5 family, and pushes the theoretical limits of what is achievable with a standard ballistic trajectory, especially when burdened with a heavy MIRV payload. Such a claim invites critical analysis of the underlying technology. One possibility is that China has achieved a major unannounced breakthrough in liquid propellant engine technology, perhaps through the development of new staged combustion cycle engines or a more energetic fuel formulation that significantly increases specific impulse. A more strategically significant and perhaps more plausible interpretation, however, is that the 20,000 kilometer figure is not a reference to a conventional ballistic range, but a signal of a fractional orbital bombardment system, (FOBS) capability. A FOBS does not follow a high arcing trajectory like a traditional ICBM. Instead, it is launched into a low partial orbit, allowing it to approach a target from any direction, including from the south over the Antarctic. This would effectively bypass the north-facing ballistic missile early warning radars that form the backbone of U.S. homeland missile defense. In a FOBS trajectory, the concept of range becomes less relevant than the ability to place a payload into a temporary orbit and deorbit it on command over a target. The Soviet Union experimented with this technology during the Cold War, and the DF-5C's immense power and payload capacity would make it an ideal platform for such a system. If the DF-5C does indeed possess a FOBS capability, it represents a profound challenge to existing missile defense architectures and adds a new layer of unpredictability to China's strategic deterrent. When compared to the flagship silo-based ICBMs of the United States and Russia, the DF-5C's unique design philosophy becomes clear. It occupies a middle ground between two distinct schools of thought on land-based nuclear deterrence. The American LGM-30G Minuteman III represents the Rapid Response School of Thought. Its three-stage solid-fuel propulsion system provides exceptional reliability and allows it to be launched in approximately 60 seconds from a state of constant alert. It is a comparatively lightweight missile, a trade-off made to prioritize speed and operational simplicity over raw payload capacity. Its current single warhead configuration is a function of arms control treaty limitations, not a technological constraint, but its design philosophy has always been centered on providing a swift and certain retaliatory strike. At the other end of the spectrum are the heavyweights, the Russian RS-28 Sarmat and the Chinese DF-5C. Both systems embrace powerful but operationally cumbersome liquid fuel engines to maximize throw weight. The Sarmat, a super-heavy ICBM with a launch weight exceeding 208,000 kilograms, is designed to carry a massive payload of up to 15 MIRVs, or Advanced Hypersonic Glide Vehicles, HGVs, along with a host of sophisticated penetration aids. Its primary purpose is to guarantee the ability to penetrate and overwhelm any existing or future missile defense system, giving Russia a credible first strike capability against even the most hardened targets. The DF-5C shares this emphasis on payload and BMD saturation, but does so in service of a different strategic goal. While the Sarmat's capabilities give it an offensive edge, the DF-5C's operational limitations, its slow fueling time, and basing posture, the shell game, firmly anchor it in a defensive retaliatory role. It is a weapon designed not to start a war, but to make the cost of starting one unthinkably high for any adversary. The Dongfeng 5C is far more than a mere modernization of an aging missile. It is a sophisticated and deliberately chosen instrument of national strategy that offers a clear window into China's evolving nuclear doctrine. It is not an interim solution or a technological stopgap, but a vital and enduring component of the PLARF's strategic architecture. The missile serves as a critical bridge, leveraging a proven heavy-lift platform to ensure the absolute credibility of China's nuclear deterrent today, while the nation continues to develop and field its next generation of more flexible, solid-fueled mobile systems like the DF-41. Its existence confirms China's unwavering commitment to maintaining a robust nuclear triad, with the silo-based leg providing the heaviest and most overwhelming retaliatory punch. The entire ecosystem surrounding the DF-5C, from its hypergolic propulsion and advanced MIRV package to its ambitious silo shell game, is a masterclass in strategic coherence. The design philosophy that sacrifices rapid response for massive payload is perfectly complemented by an operational doctrine focused on survivability through deception and cost imposition. Together, these elements create a resilient second strike force that is designed from the ground up to be both survivable against a preemptive attack and capable of saturating the most advanced missile defenses. The missile's public unveiling was, in itself, a strategic act, a form of coercive diplomacy designed to signal to the United States and the world that China has achieved a new echelon of nuclear deterrence, fundamentally altering the strategic balance of power. Ultimately, the greatest significance of the Dongfeng 5C may lie in its profound irony. In an era defined by the pursuit of hypersonic speeds, stealth, and rapid mobility, China's most formidable tool for guaranteeing retaliation and overwhelming the defenses of its primary adversary is a meticulously re-engineered, liquid-fueled relic of the Cold War. It stands as a powerful testament to the principle that in the unforgiving arena of strategic competition, the most effective solution is not always the newest, but the one most perfectly tailored to the problem at hand.